In this video, we will talk about problem D, learning to paint from CodeTON round 8. You are given an array and you can pick out a subset of its elements and color it red. Then, once you are done with the coloring, you figure out all the maximal length subarrays that are colored red. And each such subarrays will have a certain profit associated with it. And the final beauty of this configuration is equal to the summation of all these profits. Your goal is to find out the K maximum beauty across all the configuration. So for example, in this configuration we have three different subarrays that are colored red. So we will have a total of three different profits. We will sum them up to get the beauty of this particular array. The goal of this video is not to discuss the entire solution in detail. If you are attempting this problem, I am sure that you are already competent enough to read and understand the official editorial for this problem or understand the logic by going through the code that I would provide at the end. Instead, in this video, I want to walk you through the process and the techniques using which you could have solved this problem on your own during the contest. This should give you an opportunity to reflect upon your shortcomings so that you have better chances of solving such problems in future contests. The problem statement is a bit intimidating because the problem authors also need to add the formal definitions. But your goal should be to trim down the statement as much as possible. So this is the visual representation of the problem. You have colored a subset red and this subarray has a cost that is given to you, and you repeat this summation of cost for all the red subarrays and you will get the cost of this particular configuration. Now, I have talked about this fact in my previous videos as well. That is, there is a one-to-one mapping from subsets to subsequences. So, instead of talking about subsets, let us start talking about subsequences from now on. How is this helpful? It's because subsequences are ordered. Therefore, it is easy for our brains to process subsequences and devise algorithms for it. So this is the final trimmed down version of the problem. That is, you color any subsequence red and then every maximal red subarray will have some profit. You need to find out the K maximum profits that are possible across all the configurations. Now, since we are dealing with subsequences, it is natural to partition the configurations into two disjoint classes. So we can define in dp of I to be the answer for the ith prefix when the ith element is necessarily colored red. Similarly, out dp of I is the answer for the ith prefix where the ith element is necessarily colored white. And when I talk about the answer for the ith prefix, I mean all the possible configuration values for this particular prefix. Where does the intuition for this DP definition come from? You might have solved DP problems where you make a certain choice on some element. You decide to take it or you decide to leave it. So this is the same technique applied here as well. Now, how do we perform the transitions? First, let us talk about out dp of I. So this means that this element will necessarily be colored white in all of those configurations. But we do not care about the color of the I-1th element. So since we already have the configurations where the I-1th element is red or white, we can simply go to all of those configuration and append a white element at the end without adding any more profit. So that is why it would simply be the union of these two values. But notice that if you do a union of these two values, then the size of this out dp would grow exponentially. But remember that the problem only asks you to print the k maximum elements. So we can use a heap with size at max k, and as soon as the size of the heap grows to more than k, we will remove the smallest element of that max heap. So in this manner, we will ensure that in dp and out dp, they will represent max heaps whose size will never grow to more than k. Now, where does the intuition of this come from? That is, how did I think of keeping a max heap and trimming down the smallest element if the size grows to more than k? It's from experience and having solved a problem earlier where the problem statement was to keep track of the maximum k elements seen so far in an online fashion. So this is a fairly common technique if you are not aware of it. What about the transitions for in-DP? For in-DP, we know that the ith element will be necessarily colored red. Then where can the location of the last white element be? It can either be at this position or this position or this position and so on. So it can be at any index j which is strictly smaller than I. Then if the last white element is at index j, then it means that this entire subarray is red. So we need to add the profit of this red subarray to all the elements in the out dp of this jth element. So that is why we have out dp of j plus the profit that we get from the red subarray, and then we will iterate j to all the elements that are strictly to the left of the ith element. Now where does the intuition for this come from? Like, how did I know that I need to look for the last white element in the prefix? It's from experience by solving these two problems in the past. So one is array collapse from Codeforces and one is Christmas present from @coder. And both of these problems used the same logic of looking for the last xth kind of element in the prefix. So I also have a video editorial for these two problems on my channel. You can check it out if you want. Next, I decided to validate my DP idea by writing the code for n-cube solution. But note that this might not always be the best strategy for future problems. That is, you don't have to write the code for every suboptimal solution that you come up with. Sometimes it's better to take a break and think about how to improve your algorithm without directly jumping into the code. But it worked out for me, at least for this problem, because there was a clear path ahead for optimization. So first we write a function add that will take a multiset and insert a value into the multiset, while also ensuring that the size of the multiset never grows to more than k. Then we initialize the in dp and out dp multisets and start adding elements one by one. As discussed earlier, to populate out dp of I, we will take contributions from in dp I-1 and out dp of I-1. And of course, to populate in dp of I, we will iterate over all the elements to the left of I and call it j, and we will consider j to be the index of the last white element. So therefore, we will iterate over all the out dp values of j and take contribution from there by adding our own profit of the red subarray that appears as a prefix. And finally, we will look at the in dp n-1 and out dp n-1 and we will take the maximum k elements from this multiset at the end and we print it. The time complexity of this solution is n cube because we have 3 nested for loops, right? So this loop runs for n times, and this can also run till O of n, and this out dp can contain a maximum of k elements and k is of the order of n. So this is O of n cube. So this algorithm is correct but inefficient, and we need to come up with an optimization strategy for this particular algorithm. While populating the in-dp value of the ith element, we iterate over all the indices that are strictly less than I, and for the jth element, we iterate over all the out dp values and add some delta to all of this element and transfer this element over here. And what is that delta? That delta is equal to the profit of this red subarray. But notice that the final size of this red container over here is at max k. But in the worst case, we end up scanning n into k elements, because each container to the left will have a maximum of k elements, and there can be n containers in the worst case scenario. So how do we optimize the algorithm to not scan all the elements? Notice one observation, that if an element from this particular container is rejected, and by that I mean that it is not added into this red set because all the k elements are greater than this element over here, then all the suffix, that is all the elements in this container that are smaller than it, they would also be rejected. So no point in iterating over them. Similarly, for this container, a set of suffix elements will always be rejected. Same for this and same for all the containers. Now, what if there was no delta? Because this delta is confusing, because the delta value will be different for all the containers. For this container, the delta is the profit of this subarray, but for this container, the delta value is the profit of this subarray. So if there was no delta, then from experience of solving this merge k sorted list, which is a famous interview problem on LeetCode, I knew that we could solve it in k log n by adding the representative of each of the container in a max heap. Then from that max heap, you pick out what is the maximum element, or what is the maximum element from any of the representatives. So this is the, if this is the maximum element, you transfer one element from here to here, and then you delete this element from this representative. Then you repeat the whole process again for k times. So in this manner, you will only need to iterate over the elements that will for sure be accepted in your container. You do not need to iterate over redundant elements anymore. So since this is a standard problem, I will not dive into the details of this problem. But now for this particular problem, there was also a delta that needed to be added. But my intuition said that the same algorithm should work with a different delta for each of the containers as well. And upon doing some research on paper, I figured out that it should work, because you can add this representative in your max heap, but you can say that the comparator for the max heap will say that this particular container is bigger than this container if the element on the top of the container plus the delta for this container is bigger than the element at the top of this container plus the delta for this container. So all I needed to do was figure out how to create custom comparators for the max heap that I was going to use. For this part, I did not need to do a lot of research because I had already solved a problem on Codeforces called minimal labels. And this is the only problem that I have solved that uses a custom comparator for sets. So I pulled up the submission for this problem, and now I had the template that I could use to create custom comparators for sets. So essentially you need to use this declare type keyword and the lambda function that you create over here and here. Now that I had the template, I needed to figure out the parameters that I will add in the representatives. So of course the iterator and the delta value needs to be there, but I figured out that I also needed to add the index j. Why is that so? Because once you transfer an element here, you will need to increment the iterator to virtually delete this element, right? Because it is a multiset. So you don't really need to delete that element, and actually you can't delete that element because you need to keep this set intact for the I plus 1th DP transitions. So that is why you can use the trick of advancing the iterator, which is just like deleting an element. But once you are advancing an iterator, how do you know that all the elements in this set have been virtually deleted? For that, you would need the container.end reference. So that is why I added the j index over here so that I can access the container and figure out if the end has been reached or not. And finally, I also needed to know the data type of the iterator, because most of you might have been using auto itr is equals to something, right? But you cannot write the auto keyword while declaring the custom type that you will use in your set, right? But lucky for me, I was already aware of what exactly the data type of an iterator is, so it wasn't much of a challenge for me. So finally it was time to combine everything and write the final version of the code. This is our custom comparator. We figure out the iterator and delta value of both the representatives, add them up, and say whether x is greater than y depending upon whether we want a max heap or a min heap. So since I wanted a max heap, by default I added this greater than sign. And using my template, I was able to create and initialize the set with the custom element. So this is the custom element with the iterator and the delta and the index. I then iterated over all the possible j values and added their representatives into the set. Then I repeat this process k times, and in each of the operation I will pick up the representative which will give me the maximum benefit, which will of course be at the front because this is a max heap, and I remove that representative from that max heap. And then once that is done, I can add that ITR value plus the delta. This is the profit of that red subarray, and once that is done, I can virtually delete that element, and if all the elements have not been deleted, I can add that representative back. So now the time complexity of performing the transitions for in DP is now k into log n, which is sufficient to pass this problem. I was able to get an AC verdict using multisets during the contest. But there could be scenarios where the constant factor of multisets is too high and you are actually supposed to use a priority queue. But in our algorithm, it is not so easy to switch to heaps because our algorithm also relies on the fact that we need to virtually delete the element. Note that you cannot actually delete the element because you need to retain the state of the container as it is so that the I plus 1th transition can happen. So it is a dilemma, that is you need to delete the element in a heap to access the inner elements of the heap. But if you delete the element of a heap, then you are messing the state of the container and your I plus 1th transitions will not work as expected. So it looks tricky at first, but it is actually easy to incorporate heaps into this algorithm instead of multisets if you think about it. And I was aware of how to do that if it does get a TLE, but I will leave that as an exercise for you. Let me know your ideas in the comment section. This problem is a classic example of how experience and intuition can help you solve a problem. If you have solved this problem during the contest, then in hindsight it might look too easy to you, because there is virtually no step where one could get stuck. All you had to do was follow a simple rule book, and eventually everything will fall in line. But then if this problem is so easy, why does problem A has 10,000 submission but problem D only has 1500 submissions? And the idea lies in the fact that what feels standard or by the book to you might be some creative and out of the box thinking for someone else, depending upon their skill level. But if you have practiced a good number of problems, this creative thinking and intuition, this start to look like the rule book to you. For example, the first time that you use difference array to solve a problem might sound like creative thinking to you, right? But the next time you use it to solve some invariant problems, then you might think that okay, these are the standard rule of thumbs that I have created for myself, right? And that is why it is emphasized that you practice problems regularly so that you can train this skill, right? So that you can transfer from here to here. But of course, that doesn't mean that you will stop seeing problems in this bucket. And that is what competitive programming is all about. Every day you discover new ways of thinking. And Aryan also has the same opinion that not all problem will have a clear path ahead. That is, not all quadratic solution can be optimized to n log n. You might need to switch your thinking strategy to a different path. But all of this comes with experience and solving a large number of problems on Codeforces. The code for the cubic and quadratic solution, the slides, as well as the hints for this problem will be available on cfstep.com. You can also find the link in the pinned comments on YouTube.